Very good evening and welcome to the third session of the course Power Plant System Engineering. So here we will discuss the improvements in the Rankine cycle and the exergetic analysis of that. So I'll wait for one more minute, 1 or 2 more minutes maybe. Meanwhile, someone would be joined. Yeah, so here we can start our session. In the meanwhile, anybody can join. Okay, so let me go to the slides. All right. So this is the third week of the course, Power Plant System Engineering. So in the third week, we have uh, looked at the things like performance improvements in the Rankine cycle, superheat cycle, reheat cycle, regenerative cycle, then vapor cycle exergy analysis, in which we have learned the exergy analysis of different components like here we learned about the exergy analysis of these components like the heat exchangers unit, first one, the turbine and the pump and the condenser. Also we have looked into other vapor power cycles like the uh, when the working fluid will be an organic substance. The cycle is called the organic Rankine cycle. Then the binary vapor cycle, then steam cycle for nuclear power plant, then low temperature cycle and cogeneration, and then one assignment I will solve here in the class. Okay, meanwhile, let me go to the slide if someone waiting is there. Okay, waiting. Okay, so the aim of the session would be the same. I will summarize the things which happened in the uh, last week, and I will also solve some classroom and some assignment problems. Okay, so in the past week, we did not have the time to solve this problem. So I have asked to try it at home. I will not solve it here, but I had solved it myself, and I will write the hints and the final answer here. So, what they have asked in a Rankine cycle, the saturated vapor enters the turbine at 8 megapascal and saturated liquid leaves the condenser at 0.008 megapascals. So these are the two pressures they have provided. I will draw the Rankine cycle here. Okay, so this would be my temperature, this would be my entropy, and the dome something it would be look like this. Okay, so let me change the pen color. So they have asked like the steam is entering in the turbine as saturated liquid, so this point would be at this line. Okay, let me draw two pressures here first. These are constant pressure lines. Okay, so what are the two pressures they have given? P1 is equals to 8 megapascal and P2 is equals to 0.008. Let me write it bit more clearly. P2 is equals to 0.008 megapascal. Okay, so and the cycle will look like this. From this saturated vapor line, the uh, constant entropy line will go like this. Then the exit is okay. First, let me join. First, let me admit. Okay, yeah. Actually, I have already started. So what I have done in the last class, we didn't have the time to solve this problem. So what I am doing, I'm just providing some hints and the final answer. So if you have tried it, you can match or you can again try it. So this is point one, this is point two, point three, and point four. So all these things which they have asked, the thermal efficiency, back work and work ratio and the back work ratio, then mass flow rate of steam and all the things we will able to calculate once we have the enthalpy at all these 4 points. So in the last class, I have shown you how to read the values from the steam table and how to calculate the enthalpy at point 2 by using the quality of the steam x2 we have to calculate. Okay, so just I am writing the things here. H1 value will come 2758 kilojoule per kg. H2 value I have calculated and it is coming as 1798 kilojoule per kg. H3 value will come like 174 kilojoule per kg, small k, and H4 value will come 182 kilojoule per kg. I'm not writing the after decimal points. So first they have asked to calculate the thermal efficiency and it would be the ratio of network to the heat supplied. This value will come around 37%. This would be the answer of part A. Part B, you will get the work ratio as something around 99% and back work ratio would be around 87%. No, 0.87. It is 0.87. Okay. So the summation of these value would be around 100%. Okay. In part C, they have asked to calculate the mass flow rate of the stream. So this thing we can calculate as this net power is provided. So just we have to equate the things. So m dot s would come as 89 kg per second. Then in the part D, okay, A, B, C, and D. In the part D, they have asked to calculate the heat transfer rate in the boiler and the condenser. Okay, someone is there. Let me admit that first. Okay, so let me go to the slide again. So this heat supplied here, QS and QR, you will get the value of QS as 229 megawatts. Okay, as we have to multiply it by the mass flow rate we have calculated here, and the heat rejected would be 144 megawatt. The last part they have asked the calculation of the mass flow rate of the of cooling water in the condenser. So for that, just we have to equate QR is equals to m dot of cooling water into the temperature difference. Okay, the enthalpy difference, and this value will come as mass flow rate of cooling water will be 1915 kg per second. So please check these values if you get the values around that. Okay, the next problem is somewhat like this, only they have introduced the turbine and pump efficiencies. Okay, so let me draw it here. These are the two pressures, 8 megapascals and 0.008 megapascals. So my initial cycle was this 1, 2, 3, and 4. This is turbine entry 1, this is 2, this is condenser exit 3, and this is the boiler entry 4. Now, what they have asked, they have said that the turbine and the pump efficiency is 0.88. So, what you have to do, you have to first calculate this H2, then H4. Then, by using this turbine and pump efficiency, you have to calculate this enthalpy at point 2 dash, and similarly enthalpy at here at point 4 or 4 dash. So this deviation between 4 and 4 dash will come due to the turbine and pump isentropic efficiencies. Similarly, I will write the final only the final values here. So the part A, okay, first let me write all the value of enthalpies here. So the H1 value will be the same, 2758 kilojoule per kg. Here H2 dash would be different, and this value will come as 1910 kilojoule per kg. H3 would be the same as 174 kilojoule per kg, and H4 dash will come as 183 kilojoule per kg. Once you get all these values, then then you can calculate all these subparts of this question. I will write the values here. Okay. So the answer of the part A, the efficiency would be somewhat reduced. It would be 32.6%. However, earlier it was 37%. Let me write more clearly. It would be 32.6%. Earlier it was the 37% when we haven't introduced these turbine and pump isentropic efficiencies. Okay, so and the work ratio will also decreased. Earlier it was 99%, now it will 98%. The back work ratio would be 1 point something percent, or okay, it will be around, it will have around this value. Then mass flow rate of this steam will come 101.4 kg per second. However, earlier it was something less. Then the in the D part, the uh, heat supplied will come as 261 megawatt, and heat rejected would be 176 megawatt. In the last part, when you will calculate the mass flow rate of the cooling water in the condenser, it would come 2340 kg per second. So I request you to please check these values. Here my turbine work, pump work, heat supplied QS, and here heat rejected QR. So this is the stuff related to the last class. Now I'm going to start what we have done in this week. So actually in this week we have introduced some improvements, some ways by the help of which we can increase the work ratio and also the efficiency of the Rankine cycle. So the first thing we have done is that we have learned about the uh, superheating. Okay, although this is only the a simple concept, I'll show you how the efficiency and the work ratio is increased by introducing the superheating. Okay, so in the ideal Rankine cycle, let me first draw the constant phasor lines. Okay, we have seen in the ideal Rankine cycle, the uh, turbine entry point is the saturated vapor, so it is here. Okay, and the cycle was like this. This is point 1, 2, 3, and 4. So we can see that this distance is this uh, gap is less. So here the turbine work is lesser. Although while but when we introduce the superheating, superheating means the turbine entry point would be in the superheated region. So the turbine entry point would be like this, and it will expand like this. So here we got, this is point 1 dash, this is point 2 dash, this is WT dash. So here we can see that the turbine work is increased, and also it would help to increase the steam quality here. So it also avoid the erosion in the turbine blades. Okay, so this is the benefit of the superheated Rankine cycle. Also, we have learned next topic. We have seen the regenerative cycle. The regenerative cycle. In this cycle, what we do, we bleed some steam, the expanded steam from the turbine like this. Okay. So my let's suppose my Rankine cycle was like this. Earlier it was like this. Okay. So what we do in the bleeding, 1, 2, 3, and 4. Let me take the another color. So what we do in the regenerative cycle, we uh, we extract some or bleed some fraction of steam from the turbine and which is used to uh, heat this subcooled liquid. Okay, and this will go like this. So my cycle will go like this now, and and it helps in the way it increase the mean temperature of the heat addition. And in earlier we have learned that if the mean temperature of heat addition would be increased, then our efficiency will also be increased. So like the Y fraction will go to heat this subcooled liquid, and 1 minus Y part will go here, and this will be the one option only. Okay, this will again be 1, and Y fraction will go here, and 1 minus Y will go here. So, and next we have learned the thermodynamics of this cycle. It is simply the heat balance. Next is the reheating, and reheating is also done to increase the work ratio. Actually, what we do in the reheating, we expand the steam in some high pressure turbine, then again heat it, and then expand it in a low pressure turbine. We will solve some problem on this, and then we will get to have the exact idea about a reheat cycle. Okay, I will draw only the cycle here, not the different components. Okay, so how a reheat cycle look like. First, we expand it to some pressure, then we again reheat it, and then again expand it in a low pressure turbine. So here we have three pressures. Okay, the cycle will look like this: one, two, three, 4, 5, and 6. Okay, and here one work we will get from here WT1. One component of work we got from here WT2. Some heat we add here QS, and some heat we have to add here QS. So we are adding heat from 6 to 1 and 2 to 3, and from here the heat rejection would be there, and from here the work we have to supply. So let me write the equations here. So here total turbine work would be WT1 plus WT2, and it would be H1 minus H2 plus H3 minus H4. The heat addition has also increased. The total heat added would be QS is H1 minus H6. This part from here to here, and H2 minus H3, this part from here to here, plus H2 minus H3. And rest of the calculation would be the same as we have done in the earlier Rankine cycle. These are the three modifications we have learned in this week. So if you are having any doubt here, we can take that doubt. Also, we have learned some supercritical cycle where we heat the steam above this point. Okay, above this point, it will go like this. And supercritical reheat cycle and all. Then a regenerative open feed water heater and closed feed water heater we have learned, uh, and also the heat balance across that. So this is the summary of the lecture one, and based on this, I will solve a problem based on that. If you are having any problem till here, then we can discuss that. Okay, no. So let me solve this problem. Meanwhile, you can have a look at that. This is quite a lengthy problem, so it will take some time to solve. This is not the same problem. I apologize. Let me take the correct problem. Okay, so this was not the same. Yeah, so this is the different problem. Let me take the correct problem. So instead of that, here is the problem. Yeah, so this problem is asking that steam is used as working fluid in a Rankine cycle with reheat and superheat. It enters the first stage turbine at 8 megapascal and 480 degrees centigrade and expands to zero point 0.7 megapascals. Then it is reheated to 440 degrees centigrade before entering the second stage turbine. When it expands to condenser pressure of 0.008 megapascals, the net power output is 90 megawatts and each turbine operates at 88% isentropic efficiency. Then we have to determine the following parameters. First one is the thermal efficiency, then mass flow rate of the steam, then the rate heat transferred into the working fluid in the boiler and the condenser. So we'll solve this problem. Let me draw the reheat cycle first. Okay, so the reheat cycle looks something like this. Okay, suppose the first stage, a steam is expanding like this, then it is reheated, then again expanded. Okay, so this is isentropic line, and then it is condensed, then pressure increased, then it will be something like this only. Okay, so these are the three pressures. Okay, this is P1, P2. This would be my P1. This would be the intermediate pressure, and this would be the condenser pressure. So here the value is given like this: 0.1, 2, 3 would be here, and zero point 0.4, and zero point 0.5, and zero point 0.6. The processes will go like this only. Okay, so this is P1 is equals to 8 megapascals, P2 is equals to 0.7 megapascal, and P3 is equals to 0.008 megapascals. Okay, so these are the so at point 1 this thing is provided, and point 2 it is provided, and point 3 the temperature is 440 degrees centigrade and pressure is 0.7 uh, m- uh, megapascals. Okay, so what we have to find out, we have to determine the efficiency, then mass flow rate of the steam, then heat supplied in the boiler here and here, and the heat rejected. Okay, these four things we have to calculate. Let me draw the things here. Here the QS1, heat supplied 1, here heat supplied 2, here the turbine work 1 and turbine work 2. Here will be the heat rejected QR, and here will be the this will be the pump work WP. Okay, so next thing is given, like they have given these isentropic efficiencies for both the turbines. Okay, so due to those isentropic efficiencies, this point 2 would be here, some point 2 dash, and this process will come like this. Okay, so this would be 2 dash, and this line will come like this will be the point 4 dash. Okay, So our first task would be to determine the efficient enthalpies at point 1, point 2 dash 3. Okay, so okay, so this would be like this 2 dash 2 3. Okay, 2 dash 2 3. Somebody there. Okay, nobody is there. Okay, so process 2 to 3 would be like this. Then uh, let me write all the values there only. Okay, so what are the things they have given? They have given the net power output, and the net power output would be W dot net, and it would be the multiplication of steam flow rate to the specific work from turbine 1 plus specific work from turbine 2 minus specific pump work. This would be my equation 1. Okay, so first write the enthalpy at point P1. So at point at P1 is equals to 8 megapascals and 480 degrees centigrade. So this region in the superheated, this point is in the superheated region. So we have to find the values from the superheated steam table. So I have got the values from there and got that H1 would be the 3349. We write it a bit more clearly. 3349.6 kilojoule per kg, and entropy I got S1 is equals to 6.6613 kilojoule per kg Kelvin. Okay, and at point at P3, so let me write it. P2 or P3 are the same. P3 is equals to 0.7 megapascal and 440 degrees centigrade. So here the temperature is given 440 degrees centigrade. I got the values. H3 is equals to 3353.9. Okay. H3 is equals to 3353.9 kilojoule per kg, and S3 I got as 7.759 kilojoule per kg Kelvin. I have also determined the values at here at point 7 megapascal, the the values at this fluid and at the vapor point. Okay, so what I have got are that the HF at 0.7 MPa is 697. I'm not writing the unit again and again. And HFG at 0.7 is 2066, and SF is 1.99, and SFG is 4.71. Here the units are the same. The enthalpy is in kilojoule per kg and the entropy is in kilojoule per kg Kelvin. So these are the values I got for the pressure P2 over P3 is equals to zero point 0.7 megapascals. Then at 0.008 megapascal pressure, the pressure at P4, the HF value is 173.8 kilojoule per kg. HFG here is 2402.4 kilojoule per kg. SF here would be 0.5924 kilojoule per kg Kelvin, and SFG here would be 7.6348 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. And also I have to find it here the specific volume. It is 0.001008 meter cube per kilogram. Okay, so these are the things I have collect. Now here we can see that entropy at point 1 and point 2 would be the same. So I am equating that thing. We know that S1 would be equals to S2. S1 value we are having 6.6613. That would be equals to SF at 0.7. SF at 0.7 megapascal pressure plus X2 and SFG at 0.7 megapascal pressure. So we will put the values here. 6.6613 is equals to this value we are having 1.9918 plus x2 into 4.7153. Okay, here we will get the value of x2. It is coming as 0.99. Based on that we can calculate the value of h2. H2 will be HF at 0.7 plus X2 at HFG at 0.7. So this value 697 plus 0.99 into 2065.9. Okay, so H2 value is coming like 2742.7 kilojoule per kg. So this value we have determined for the isentropic process, but here the isentropic efficiency of the turbine is provided. So we will apply it here. We know that the isentropic efficiency for turbine 1 is 0.88 and the expression would be H1 minus H2 dash divided by H1 minus H2. So we will put the values here. 0.88 is equals to 3349.6 minus H2 dash divided by 3349.6 minus 2742.7. So from here we will get the value of H2 dash is equals to 2815.52 kilojoule per kg. Okay, so like here we got the value of H2. Similarly, what we have to do, we have to equate the here we have to equate S3 is equals to S4. In the same way we will calculate the H4, and by applying the isotopic efficiency we will be able to get the H4 dash. Okay, so here I will not write the complete things. While we will equate S3 is equals to S4, the expression would be 7.759 is equals to SF at 0.008 plus X4 into SFG at 0.008. We are having all these values, so while we put the values, we will got the value of X4 as 0.9386. By the help of this X4, we can calculate the enthalpy at point 4. So the H4 would be HF at 0.008 plus X4 into HFG at 0.008. This value we will get while we put these values. The H4 would be 2428.87 kilojoule per kg. Next, we will apply the isentropic efficiency for turbine 2, which is 0.88. So the expression would be H3 minus H4 dash divided by H3 minus H4. We will put the value of H3 and H4 and get the value of H4 dash as 2539.87 kilojoule per kg. So till now we will get the values of H1, H2 dash, H3 and H4 dash, and by the help of this that we can calculate the specific turbine work. So specific specific work for first turbine, or we can say the high pressure turbine, would be WT1 is equals to H1 minus H2 dash. The values we have calculated are 3349.6 minus 2815.52. So the specific work for turbine work is the having the value of 534 kilojoule per kg. Similarly, the specific work for low pressure turbine, it would be WT2 is equals to H3 minus H4 dash. The values we have calculated as H3 is 3353.9, 353.9 minus 2539.87. 87. Here WT2 value we will get 814 kilojoule per kg. So we can also write it here. Total turbine work WT is equals to WT1 plus WT2. It would be 534 plus 814 1348 kilojoule per kg. Kilojoule per kg. So this thing we also have determined. Now the next thing is to determine the pump work. We know that specific pump work would be specific volume at point 5 here. Where it gone? At point 5, which we have determined here. Where it is? Yeah, here. So this is the specific volume of fluid at point 5, right? V5 here. Okay. V5 into P1 minus P4. Okay, so all these values we are having. We are having 0.001008. Or pressure at point 1 is 8 megapascal. Pressure at point 4 is 0.008 megapascal. Okay, to convert into the kilojoule per kg, I am multiplying it by zero point 0.3, 10 to the power 3, sorry. So here, from here, the WTP will come around 8 kilojoule per kg. Okay, so the pump work we got here. And the enthalpy at point 0.5, we already get H5 value. We are having the enthalpy at here. Enthalpy at point 0.5 is the enthalpy of saturated liquid at 0.008 megapascal pressure, and this value we have written here as the H5 is the, so this value is H5. Okay, so H5 value we are having 173.8 kilojoule per kg, and H6 would be H5 plus specific pump work. So this would be 173.8 plus 8, value will come 181.8 kilojoule per kg. So from here we got the turbine work, the pump work, and the enthalpy at all the points. Based on that, we can determine the heat supplied. Okay, we can determine the heat supplied, the specific heat supplied basically. Heat supplied QS would be, like here we are having the heat supplied H1 minus H6 plus H3 minus H2 dash. So here 2 points we are supplying the heat. So the expression would be H1 minus H6 plus H3 minus H2 dash. So I will put some values here. H1 value I am having 3349.6 minus 181.8. I just calculated, plus H3 value is 33.53.9 minus 2815.5. So the specific heat supplied in the boiler would be 3706 kilojoule per kg. Okay, this is the heat supplied. Then heat rejected. This broad Savita specific. So the heat rejected would be, from here it would be the H4 dash minus H5. H4 dash value we have calculated as 2538.87. H5 value we are having 173.8. So the specific heat rejected in the condenser would be 2365 kilojoule per kg. So like this, we have determined all the things. Now we can answer all the parts which are asked. So in the part A, what they have asked, the thermal efficiency. The thermal efficiency would be W net by heat supplied. So R W net is the turbine work minus pump work divided by heat supplied. We have determined these things as my turbine work was 1348, pump work was 8, and turbine work was 1348. So turbine work was 1348, pump work was 8, and the heat supplied is 3706, as we have determined it is here 3706. So in the percentage, this value will come around 36.15%. Okay, so this would be the answer for the first problem. In the problem B, what they have asked, the problem B, they have asked the mass flow rate. So the value of the uh, Network is given as 90 megawatt, and it can be written it as mass flow rate of steam into specific work done. Okay, so to convert it into the kilo, I will multiply it with 10 to the power 3 ms dot, and W net we are having the value of 1348. So the value of this steam will come around 66.76 kg per second. In the part C, what they have asked? They have asked the total heat supply rate. So it would be the multiplication of steam mass flow rate into specific heat supplied. This would be the 66.76 into QS value we are having 3706, and I will multiply it by 10 to the power minus 3 to convert it to the megapascal. Okay, so this value will come around 247.43 megawatts. And part D, the heat rejected would be mass flow rate of steam into the specific heat rejected. This value I am having 66.76 into heat rejected. We have just calculated 2365 into 10 to the power minus 3. This value will come around 158.84 megawatts. So these are the four things they have asked us to calculate, and we have calculated. So this is will be the final answer. Okay, so in this problem we have started with the reheat cycle. We have incorporated the turbine efficiencies, cal calculated enthalpy at all the points, and then answer the four questions: the thermal efficiency, the mass flow rate of the steam, the heat addition rate, and the heat rejection rate. Okay, so that's it. Next, we have looked into the exergy analysis of the vapor power cycle. Okay, then we have written the different formulas for the exergy calculation, exergy destruction, exergy efficiencies for different components like boiler, turbine, and pump, and the condensers. And based on that, a problem is there. It is also solved in the class. So this problem is simply the formula based. You will try it, and if you will have any doubt, then we will discuss this in next class. Okay, here simply you have to apply the formulas. Enthalpy for all the processes is provided here, so you don't have to look for any uh, steam table to get the enthalpy values for that. Okay, so these three problems are connected. I'm not having the time to solve all of them, so you please try it, and if you will have any doubt, then we will discuss. Or even I can write the formulas for these things. No, but all the formulas are provided in the lecture, so you can refer that. Yeah, the most important thing, what I have to do, I have to solve some problems for you. Okay, so first problem, it is saying like that the Rankine cycle is operating under the same pressure conditions. Okay, if superheating and reheating are done, then turbine work will be decreased. Okay, it is not correct. So this statement is false. We have seen that when we apply the superheating and reheating like this, when we applying the superheating and reheating, then the turbine work will increase. Okay, so this is temperature, entropy. So it's point 1, 2, 3, 4, 5, 6. So here we will get the turbine work from here point 1 to 2 WT1 and point 3 to 4 WT2. So this will be added. So net turbine work would be increase. Okay, not decrease. So this option is not correct. It is false. Next, in a reheat cycle, the steam expands to condenser pressure in a single stage. No, this is also not correct. This is false statement as we have seen in the reheating cycle. If this is my reheating cycle, then we bleed some steam from here and then it match like here, then it will go like this. Okay, so we bleed some fraction from it and rest of the steam is expanded to the lower pressure P2. Okay, so this statement is false. Next is a double pump is used in the following cycle. So in the lecture we have seen that in regenerative cycle we have to use the double pump. As we can see here, one pump would be here. Okay, let me draw it here only. Okay, so if this is my regenerative cycle, so first pump would be applied here. Yeah. Yes. So this is point 1, 2, 3, 4, 5, 6, 7. Okay. So one pump would be here, WP1 work, and one pump would be here, WP2 work. So and Y fraction would be go here, and 1 minus V would be expended fully in the turbine. Okay. This is 1 minus Y. It's not very clear. Okay, so this is 1 minus y. 1 minus y will expand here and y fraction will go here. Okay, so here a double pump is applied in the regenerative cycle. Next, when a system is at dead state, the system is at dead state. First option is it is in a thermal equilibrium with the environment. Correct statement. It is in a mechanical equilibrium with the environment. Exergy is zero. Okay. So all these options are correct. So the correct option would be all of the above. So when a system is at dead state, uh, it is in thermal and mechanical equilibrium with the environment, and the exergy would be zero. So option D would be the correct option. Next problem, which of the following statements are true for a binary vapor cycle? Okay, so in the binary vapor cycle, basically we use two cycles, the uh, high pressure and the low pressure cycles. If I am having that figure here, I will show you. Yeah, so here I'll try to draw the binary cycle here. There would be a upper down. Okay, cycle would be like this. Okay, and the lower cycle would be like this. Let me choose another calculator. Okay, so this is first cycle. This would be the second cycle. It will go like this, and this will go like this. This is the TS diagram. This is called the topping cycle, and this one is the bottoming cycle. What happened in the binary cycle is that this heat rejected here is act as the heat supply to the bottoming cycle. So this is, let's say this cycle is 1, 2, 3, 4. The cycle is A, B, C, D. So this condenser for the bottoming cycle act as the condenser for the topping cycle act as the boiler for the bottoming cycle. So like this we can utilize the heat rejected in this high pressure high temperature cycle here, and the heat rejected would be supplied to the bottoming cycle. So what are the options provided for this problem? Which of the following statements are true? First one, it couples two vapor cycles. Correct. Two ideal Rankine cycles are combined using an interconnecting heat exchanger. Correct. So this is the interconnecting heat exchanger. This option is also correct. And the heat is rejected from the topping cycle provides heat input to the bottoming cycle. So this option is also correct. So here also all the three options are correct. Here also all the three options are correct. And moving to the problem number 6. Okay. Here what they have said, the exergetic efficiency is always less than unity. So this thing we have seen in the exergetic efficiency always less than unity. So this option is correct. So till here, we are done with the theoretical questions. Now, there is a series of numerical questions from problem 7 to 10. So I will solve these questions for you. Okay, so let's take 2 minute break and then I'll start. Okay, so here we go. So what is said here, in a Rankine cycle, the saturated vapor enters the turbine at 78 bar and saturated liquid leaves the condenser at 0.1 bar. The net power output of the cycle is 93.22 megawatt. Okay, 1 megapascal is equals to 10 watt. It is understood. In condenser inlet and outlets, these are the values. I don't think these values we will use in this problem. And the thermal efficiency we have to calculate. So first let me make the cycle. It is mentioned here that the turbine, the saturated vapor is entering to the turbine. Okay, so the cycle would be like this. Point one would be somewhere here because the saturated vapor is entering to the turbine. Okay, now it will be go through the condenser and then the boiler would be like this. Okay, so this would be my cycle. This would be temperature and entropy. This would be point 1, point 2, point 3, and point 4. Here, the specific turbine work will be get and specific pump work we have to supply. Here, specific heat we have to supply, and here, specific heat would be rejected. Okay, so these four processes would be there. Okay, so here two pressures are there, like pressure P1 is 78 bar, which would be equivalent to 7.8 megapascal. Pressure P2 is 0.1 bar, which would be equivalent to 0.001 megapascals. Okay, so these things are provided. Also, the net power output is provided, which would be W capital W dot net. It is provided 93.22 megapascal or 93.22 into 10 to power 3 kilopascal. Sorry, 93.22 megawatt or 93.22 into 10 to power 3 kilowatt. Okay, so these are the things they have provided. Now, how we have to start? We have to get the enthalpy at all the points. So, at E1 is equals to 7.8 MPa. This is the vapor phase. So here H1 would be directly could be calculated, and it is 2761.6 2761.6 kilojoule per kg. Entropy here is 5.7586 kilojoule per kg Kelvin. At P2 is equals to 0.01 bar MPa, sorry, at 0.01 megapascals. H3, it would also be HF. Write it clearly. H3 is equals to HF equals to 191.81 per kg. HFG provided 2392.1 kilojoule per kg. SF here is 0.6492 kilojoule per kg Kelvin, and SFG is 7.4996 kilojoule per kg Kelvin. Okay, so these value would help us to determine the enthalpy at point 2. Let me first get the uh, quality or vapor fraction at point 2. So let me create. We know that S1 would be equals to S2. Okay, and here S1 is, this is 5.7586 is equals to SF would be 0.6492 plus X2 into 7.4996. So the X2 would be equals to 0.6812. Okay, I got the value of the quality of the steam at point 2. Okay, so I'm solving this problem basically. So Here the H1 value I got directly, H3 value I got directly. In order to calculate the enthalpy at point 2, I have calculated the quality of the steam at point 2. Now, by the help of this HF and HFG, I would be able to calculate the enthalpy at point 2. Let me do it on next page. Okay, so what would be the expression for H2? H2 would be HF plus X2 into HFG. I will write the values here. HFG here. Sorry for my writing. So it would be 191.81 plus 0.6812 is value of X2 we got on the previous page. Then 2392.1. From here, H2 value I got is 1821.52 kilojoule per kg. Also, I can determine the okay. So I got the value of H1 and H2. Now I would be able to determine the specific turbine work here. So the turbine work, turbine work specific, I would write kilojoule per kg. So the WT here would be H1 minus H2. H1 value I had 2761.6 minus H2 value I have just calculated 1821.52. This will give me the value of 261.6 minus 821.52 940. This is 940 kilojoule per kg. Similarly, I can calculate the pump work. Expression for the pump work would be the specific volume at point 3 into pressure at point 1 minus pressure at point 2. Specific volume at point 3, I am having the value of 0.00101. To pressure at point 1 is 7.8 minus pressure at point 2 is 0.01 megapascal. To convert into the kilopascal, I will multiply it. Okay, I will multiply it by 10 to the power 3. So the pump work I will get from here is 199.67 kilojoule per kg. Based on this pump work, I can calculate the enthalpy at point 4. H4 is equals to H4 will be S3 plus pump work. S3 value I am having 191.81 plus pump work. Okay, so yeah, this is not correct. Let me calculate it. 7.8 minus 0.01. 0.0001. This is 7.86. Okay. Pump work is, I'm sorry, 7.86 kilojoule per kg. Okay. And when I will put this value here, value will come out to be 199.67. The value at H4 enthalpy would be 199.67 kilojoule per kg. So now I have calculated the enthalpy at point 4 also. Now the network would be network W net is the turbine work minus pump work. What it is? It is 940 minus 7.86. This value will come out to be 932.14 kilojoule per kg. The heat added or heat supplied, what it would be H1 minus H4. H1 value we are having like 2761.6 minus H4 value is 199.67. So this value would be 2561.93 kilojoule per kg. Then heat rejected QR would be H2 minus H3, and this would be the heat rejected in the condenser, or also we can say the condenser rate. H2 value we are having 1821.52 minus H3 value is 191.81. So this value will come out to be 1629.71. Okay, maybe 1629.71 kilojoule per kg. So, like here, I have calculated all the things: the network, the heat supplied, the heat rejected. Now we can answer the questions asked one by one. So, in the first problem, what they have asked for the thermal efficiency or the cycle efficiency. So, the thermal efficiency would be the network divided by the heat supplied. The values we got like 932.14 for the W net. It is 932.14, and the heat supplied is 2561.93. 561.93. 561. Visible? No. It is 2561.93. I'll multiply it by 100 to convert into the percentage. Thermal efficiency will come around 36.38. Okay, so this would be the answer of this particular subsection. Answer would be 36.38. 36.38%. Okay, so this would be the answer. The next problem, what they have asked to calculate the mass flow rate of the steam. So what they have given that the net power output of the cycle is 93.22 megawatt. What they have given, W net is equals to 93.22 megawatt, or 93.22 into 10 to the power 3 kilowatt, and it would be equals to the mass flow rate of the steam into specific net work done. I will put the value here 93.22 into 10 to the power 3 equals to mass flow rate into the W net we just got as the we get the W net value is 932.14 is the 932.14. So from here we'll get the mass flow rate of the steam is around 100 kg per second. Okay, would be around the exact value. It would be the 100 kg per second. This would be the answer for the problem 8. Okay, following the next, what they have asked the rate of heat transfer to the working fluid in the boiler. So what they are asking, the heat supplied rate in the boiler. We are having the steam mass flow rate. We have just calculated 100 kg per second. So this heat added rate into the boiler would be m dot s into specific heat supplied. This would be 100. This QS we have just calculated as the 2561.93. Okay, so the value will come around 256.193 into 10 to power 3 kilowatt. Don't confuse with the unit of this, right? The unit would be kg per second into kilojoule per kg. Kg to kg cancelled, and this would be the kilowatt. Okay, so kilowatt would be the final unit, or we can also write it like this: Q dot S is equals to 256.19 megawatts. Okay, as they have asked the thing in the megawatt, so this would be the 256.19 megawatt. Okay, so moving to the last problem. Here, what they have asked the heat transfer to the working fluid in the condenser, or the heat supplied in the heat transferred in the condenser. Basically, it is the heat rejected in the condenser, which we have the specific thing we have already calculated. We have calculated the mass flow rate of steam is 100 kg per second, and the Q dot rejected, which they have asked, heat transfer in the condenser, it would be the m dot s multiplied by QR. This would be 100. QR we have already calculated as 1629.71. 1629.71. Okay, so this value would be 162.971 into 10 to the power 3 kilowatt. The thing is asked in the megawatts. So in megawatts, it would be Q dot R is equals to 162.971 megawatt. This would be the answer. 162.71 megawatt. So these are the 10 problems I want to discuss. Okay. And I request you please try these three interconnected problems. These are simply only the four formula based. I don't have the time to discuss all these things. Okay, I have solved this big problem. You can go through it, and in the next class also, if you are having any doubt regarding this problem, then we can take that out and summarize the class. I have uh, shown the way by the help of which we can solve the unsolved problem in the last session. So like this, you can solve that, and I have just explained what are superheating, regenerative, and the reheating cycles, and that's it. Okay. Okay. So thank you for joining. Yeah. Thank you. We'll meet in next class. Thank you.